As we mentioned before, Arch1 model is a very simple type of arch model family, and it has only one lag term. In practice, usually you have a multiple lag terms. That will be just give you a natural extension of the case with just one lag, or the Arch1 model. Just like the one on the slide, you can consider lag length up to Q. Although in theory it's a natural extension, in practice, the estimation of such model is quite tedious, simply because you have so many parameters to be estimated, and interpretation of those coefficients is not going to be very straightforward. So it's both clumsy and inconvenient. This is why we are going to introduce the so-called generalized arch model, or GARCH model. That is an alternative way to estimate exactly the same model, but it's operational-wise is easier to implement, and is also intuitive, easier to explain. So if we have an ArchQ model, we can rewrite the ArchQ model as this one. So we just keep inserting those terms into this equation and then rearrange it. That basically gives us this equation. So an ArchQ model actually is an GARCH 1-1 model. It contains lag one terms of ET and HT. So it's a combination of the error term in the last period, also the value of HT itself in the last period. So this ET is kind of a short-term shock from the last period. The time series can still remember it. That makes sense. Actually, that's the part that we include in an Arch1 model. The second part is interesting. It basically tells us kind of a momentum effect there. So the H series itself can remember what happened to itself, not just the shock from the time series, but also the time series of the volatility itself. It's kind of hidden in the time series. So intuitively, that makes sense. And by comparing those two coefficients, we can actually tell which part has a bigger impact, relatively speaking. It's either the short-term shock from the error term, or the historical, or the past, or the momentum effect from the variance series itself. So for an GARCH model, it is very popular because it fits many data series well. In practice, this is just a model that is very convenient to estimate, and it makes sense. It tells us that the volatility changes with the lagged shocks, that's ET minus 1 square. But there is also momentum in the system working through HT minus 1. So HT minus 1, bear in mind that it's not the same as ET, because ET is the shock and HT minus 1 is the variance of that shock. Those are two different concepts. And one reason for this model to be so popular is it can capture long lags in the shocks with only a few parameters. So it's equivalent, in theory, it's equivalent to an arch model with a very long lag, because Q could be quite long, but doesn't matter how long it is. It can be, in theory, it can be converted into a GARCH model, and we only need to estimate 2 parameters. So that's very attractive. Now let's use this brighten your day lightning company's stock price to illustrate how to estimate a GARCH model. Once again, we assume the return, the average is constant. It doesn't change over time in theory, but you do have shocks. So the mean is the same as 1.049. But now look at this equation. That's the stochastic process to generate HT this time series. So besides an arch element, we also have a GARCH element there. So this is called arch element. That's in our arch model that we discussed before. On top of that, we have another one that is coefficient of the lag term of HT hat. That's the GARCH element. And both of them are significant over time. And this is the prediction, or the estimated variance over time. So the mean is constant, but the variance isn't. It changes over time. That's the estimation of Gauge model. And later I'm going to demonstrate in Stata how to estimate a Gauge model. The next extension is the threshold arch model, or T-arch. It's very useful in practice because the market's response or people's response to positive and negative news are not the same. They are usually treated asymmetrically. And generally speaking, people respond to negative news stronger than positive news. So that's based on some empirical observation, and that's why this T-arch model sometimes fits the empirical data better than a general arch model. So in the Gauge model, we are going to add one more term over there. So D here is a dummy variable, or is an indicator. It takes value of 1 and 0 only. It equals 1 when we have bad news. It equals 0 when we have good news or otherwise. So we focus on bad news, and you can expect that this gamma should be positive if this assumption is true, which means when we have negative news, our response will be stronger. So this part, gamma, will add up to alpha 1. In other words, the coefficient, this here, alpha 1, is our response to good news. And then if there is any negative news, our response will be alpha 1 plus gamma. So that's the interpretation of this model. And this can be easily estimated in Stata as well. So this is the T-Gauge model. If we use the Brighten Your Days Lightning stock price as an example again, our estimation, it will change the mean slightly because both of them are estimated jointly. So if you put this into the equation, inevitably, it will change the coefficient estimate even if slightly. So it changed from greater than 1 to be smaller than 1, but the change is quite marginal. And in our random process to generate HT, we have the arch element here, that's 0.263. We also have a gauge element over there, it's 0.287. On top of that, we also have this threshold element there, and that's attached to this dummy variable. So that means if we have a negative news, the response actually is quite big, it's 0.492. On top of this 0.263. So for good news, our response is 0.263, but if it's negative news, it will be 0.492 more. So that's the explanation of this regression, of this estimation, and the estimated variance are given here as well. The next extension is Gauge in mean model. So it captured the relationship between risk and return. So both variance and means are allowed to change over time. So if we look at the functional form here, y is not a constant anymore. Previously, we do not have this term over there. And now we add this over here. So essentially, it means people actually look at the volatility of the time series or the stability or riskiness of the market, then decide how much they pay. And we understand some basic principle in investment is return and risk are always positively correlated, one-to-one, almost. It's not one-to-one, but it's closely related. For example, if it is high risk assets, your requirement for the minimum rate of return will be higher as well. Otherwise, it will not compensate for the risk that you're going to take. On that note, we will rationally expect that return, or YT, is associated with HT, and that coefficient theta probably is positive. Is it true? Let's have a look. So we use this BYD stock price as an example as well, and then we estimate this Gauge in mean model. We still keep this threshold elements in here. So we'll just keep expanding the model. The mean is estimated as this one. So it's as expected. We have a significant coefficient and it's positive, which means if the volatility is high, we expect the return is high as well. Then we have the estimation over there. So the coefficients are slightly different from previous one, but the conclusion remains the same. We still react to negative news much more strongly than positive news. And we do have both arch and the gauge effect that are significant in our model. And you may notice that when we plot the value of return and the value of volatility, both of them are not constant over time.